Hi, today's chapter is chapter 3, which is called three-phase AC induction motor. So there are lots of application of three-phase induction motor to name that can be used in the electrical train engine, cooling fan used to cool large machines like alternators, chimneys at power plants, printing machines, and rolling mills. At the end of the chapter 3, three-phase induction motor, students will be able to gain this knowledge. We will go one by one. So 3.1, I will talk about the construction of induction motor. A typical motor consists of two main parts separated by a small A gap. Here, small A gap between stator and the rotor. This is the stator. Stator is known as the stationary part, while rotor is known as the rotating part. A stationary stator having coils supplied with AC current to produce a rotating magnetic field, or sometimes the abbreviation is RMF. The rotor will attach to the output shaft that is given a torque by the rotating field. This is the picture of the stator construction. The stator is laminated iron core with slots. Coils are placed in the slot to form a three or single phase winding. The coil used is copper. So the two types of rotor construction that can be found in an induction motor. One is a squirrel cage rotor and another one is the wound rotor. Squirrel cage rotor is a no winding and no slip ring, also known as a brushless induction motor, while for the wound rotor is a three-phase winding, usually Y connected, and at the end of each phase and winding are connected to a slip ring, which is also known as a slip ring motor. So this is the slip ring. Since it is a three-phase, so it possesses three slip rings. This is the example, the picture of the squirrel cage rotor, and this is the wound rotor. So you can see the video of the principle of operation for the induction motor available at my Microsoft team. I had downloaded it from the YouTube. Hope you will gain more knowledge about the operation of induction motor at there. 3.3, I will talk about the slip and slip speed in induction motor. Flux rotates at a fixed speed known as a synchronous speed, or the rotating magnetic field. The speed of the rotating magnetic field is also known as the synchronous speed. Synchronous speed is also known, the abbreviation is NS. The formula is NS is equal to 120 times F over P, which is F is the supply frequency, P is the number of poles, and S is synchronous speed, as I mentioned earlier. The slip speed defined as a difference between the rotor speed and the synchronous speed. Mathematically, it can be written as here. N slip is equal to NS minus NR. Slip is the ratio of the speed difference between synchronous speed and rotor speed to the synchronous speed, which can be given by S is equal to NS minus NR over NS, which is S is the abbreviation of the slip. Usually, the value of S is between 0 and 1. In most cases, at no load, the slip is 0. At full load, the slip for large motor will rarely exceed 0.5%, and for small load, at full load, it rarely exceeds 5%. The rotor at standstill, which is while the rotor is locked, the slip is 100% or unity 1. Slip and slip speed in induction motor, they continue. Using the ratio of slip, the mechanical speed of the rotor in terms of speed and synchronous speed can be written as this equation. This equation is a manipulative manipulated from the equation previously, ns minus nr over ns. So I rearrange this formula, thus I will get this equation. So you can only memorize one formula which is suitable for these two formulas. And this ns, the unit is in RPM. ns, nr, the unit is in RPM. While for the omega, is the angular velocity, the unit is in radian per second. So omega s is stand for synchronous speed, omega r is stand for rotor or motor speed. If you observe, these two possess the same equation, the same formula, it's just the denote is different. Instead of using n in RPM, they are using omega in radian per second. The voltage and frequency induced in the rotor both depend upon the slip, whereby the frequency of the rotor is equal to slip times frequency of the synchronized. So frequency of the synchronized speed is 50 Hertz. Okay, this is the frequency used in TNB for synchronization of the electrical power. And E2 is the internal induced voltage. E2, voltage induced in the rotor at slip, is equal to slip times open circuit voltage induced in the rotor. So here is the one example involving the calculation for NS and slip. A 0.5 horsepower 6-pole induction motor is excited by a 3-phase 60 Hz source. If the full load speed is 1,140 RPM, calculate the speed. So first thing first, in order for you to calculate the slip, which is S, you need to obtain the value of NS first. So by using this formula, NS is equal to 120 times F over P, you will get the value for NS, which is 1,200 RPM. And now, here at the question, it's already given the value of NR, where it stated that if the full load speed is 1,140 RPM. So you just insert the value in this equation. Slip is equal to NS minus NR of NS. You will obtain the slip is 5%.